All right, good morning. Today we're talking about exponential and logarithms. And to get started, we need to talk about how exponentials and logarithms are inverses. They are inverses of one another. If you remember back from Unit 7, we talked about how inverses reflect over the line y equals x. And so exponential graphs and logarithm graphs actually do that. Okay, so this is our y equals x. That would be our reflection line. And so we're just going to look at this kind of quickly, relating back to our exponential graph, where we know if we plug in 0, anything to the 0 is 1. And if we plug in 1, 2 to the first is 2. And then this would be 4, and that would be 8. And then if I plug in -1, it would be 1/2. And so we can get the exponential curve just like we did the other day. That looks something like this: 2 to 4, 3 to 8. And so the curve is flat, close to that x-axis, and then it curves up and grows exponentially. And so this would be f of x right there. So the inverse of f of x is log base 2 of x, where if I take this function, my original f of x, and I switch x and y, I have all of the same numbers except they switch the place that they're in. So it's going to be 1, 0, 2, 1, 4 and 2, 8 and 3, and 1/2, -1. And so when we go and graph those, since again we're just switching x and y, we get 1, 0, 2, 1, 4, 2, 8, 3, and 1/2, -1 would be right there. And so this curve looks like, ooh, and I was drawing it wrong, right here. And then what's different is I still need to hug that line, but now I'm not going to be able to cross the y-axis instead. Okay, so f of x was originally a growth function. It had a turning point of 0, 1, just like we talked about the other day. The asymptote was at y equals 0. The domain was everything, and the range was 0 to infinity, but not including 0. Okay, and then the inverse is an important idea, where all of those things are kind of flip-flopped. They're kind of the reverse of them. So the turning point, you just again switch your x and your y, and so it'd be 1, 0. The asymptote, instead of x or y equals 0, it's going to be x equals 0. So that'd be a vertical asymptote. And then the domain and the range are going to switch. So the domain is now 0 to infinity, and the range is -infinity to infinity. Okay, so they're inverses. Again, so the x and the y's just switch. And so we get these really important points for an exponential, like the turning point at 0, 1 becomes 1, 0. Okay, and it's so a reflection over the line y equals x. If we look at the second example, I have an exponential decay because this b value is less than 1 and greater than 0. And so when we graph that function, we have x, y. We're going to plug in 0, 1, -1, -2, and -3. And that's going to result in 1, 1/2, 2, 4, and 8, just like we did the other day. So I can go back and graph these. This would be 1 and 1/2, -1, 2, -2, 4, -3, 8. And so we get our exponential decay graph looks like this. Okay, so there's the decay. And then again, if exponentials to logarithms are just inverses, I can take all of my x and y values and just switch the spot that they're in, and I can get my new graph. Okay, so this would be 1, 0, and then 1/2, 1, and let's see, 2, -1, 4, -2, and then 8, -3. And so this graph ends up being, and again, I can't cross the y-axis now. It's going to be like this. Hits the turning point and curves and flattens out. And it's this is kind of weird to look at, but it is still being reflected over this line y equals x. Okay, so all that stuff is still true. So the turning point, I guess I'm going to write this every single time. Turning point was originally 0, 1, and then it's going to turn into 1, 0. So they're going to switch spots. The asymptote of the original was y equals 0, so then it turns into x equals 0 again. And then we had the original domain was negative infinity to infinity, with the range being 0 to infinity, and then again those just flip-flop. So it's 0 to infinity for the new domain and negative infinity to infinity for the new range. Okay, so the main point is exponential logarithms are inverses. It reflects over the line y equals x, and you switch your x and your y, and you can go and graph it. Okay, so the inverse of y equals b to the x is x equals b to the y, switching your x and y. And so for x equals b to the y, the variable y is called the logarithm of x. Okay, so logarithms solve for the exponent of the equation in exponential form. So that'd be y equals log base b of x. Again, that's how you need to say it. So if I ever asked you to read this out loud, you would need to literally say log base b of x would be how you phrase that right there. Okay, so we have graphing logarithmic functions. So b, the base value, is still b for base. And if it's bigger than 1, you're growing. If it's between 0 and 1, you're decaying. All kind of makes sense, but it's the curve of the actual graph itself that kind of changes. And so it's going to be important for you to remember the differences between the exponential parent function and the logarithmic parent function. Because we're going to do transformations for both, but if you start in the wrong spot, then you're going to apply the transformations incorrectly. So exponentials was y equals b to the x. Logarithmic is now y equals log base b of x. Two very different things. Okay, so again, exponential, we'll go through those key characteristics again. So we have negative infinity to infinity. The range was 0 to infinity. The asymptote cannot cross the x-axis, so that would be y equals 0. The turning point was originally 0, 1. There were some other key points of 1, b and negative 1, 1 over b. That's a 6. And over b. And it's increasing when your b value is greater than 1, and it was decreasing or decay when you're between 0 and 1. Okay, so that's all the things for exponential. But now we're going to apply our reflecting over the y-axis, or not y-axis, y equals x principle, and write the key characteristics of the logarithmic. So the domain and range switch. So this becomes 0 to infinity for the domain. The range is negative infinity to infinity. The asymptote is no longer y equals 0, but it's x equals 0. Okay, if you switch x and y for your turning point, you're at 1, 0. If you look at these two key points, you're just going to switch x and y again. So it's b, 1 and 1 over b, negative 1. And then you're increasing in the same way though. So that's b greater than 1 and decreasing when b is between 0 and 1. Okay, so they're mainly just flip-flopping the x and y values, which again makes sense because they're inverses, except be careful with your increasing and decreasing. Those are the same no matter. You just need to know what the value does. Okay, transformations, we're going to have the same types of transformations, but they're going to be located in kind of different spots, but kind of the same spots. But so if you're inside the parentheses, you're going left and right. That's like normal. The k value in the back, you're adding and subtracting, you're just going up and down. The orientation, the a value in the shape, vertical stretch or shrink, those are found using the same values. So we could stretch vertically, or again, I'm fine with you saying compressed or shrink vertically, vertical shrink. All that is found in the same way. So if we go to number 1, we have the equation y equals log base 8 of x minus 2. Okay, so first it's really important to notice, oh, this is a logarithmic function, and it's going to be a logarithmic, and since that number is 8, and that's our b-value base, and it's bigger than 1, this is going to be a growth equation. So in your brain from the very beginning, you need to be thinking, that's what my graph looks like to start, and then I'm going to apply transformations to it. So this minus 2, since it's on the inside of the parentheses, that means we're going to go to the right 2. So if we graph the parent, and sometimes I think people like this table way, where if I plug in 1, I'm going to get 0, and if I plug in 8, I'm going to get 1. So there's the parent function. So that's 1, 0, and 8, 1. And then I know I'm not allowed to cross that vertical asymptote at x equals 0. So the original parent for this looks like that. Okay. Well, if I need to push everything to the right too, well, then that's going to change the x value only. So that's going to make that a 3, and that would be a 10. And so that becomes my 2 really important points. But the big thing to remember is that now, since I have a vertical asymptote, I am pushing this vertical asymptote to the right as well. And so now it's going to be at x equals 2. So when we go to graph, we're going to go up, go up, go up, go up, hit our turning point, and then flatten out, and it's going to look like that. So it should be the same curve, just pushed to the right. So our new turning point would be at 3, 0. Our vertical asymptote would now be at x equals 2, because I pushed it 2 to the right. The domain is the x values, which should be now 2 to infinity, and the range would be everything, because I'm going up and down forever. Okay. Number 2, we're going to use this equation. You may not have it. You may, either way, if you want to scribble it out, we're going to use this one. But we have f of x equals 5 times log base of 1/9 of x plus 3. So if we're comparing and contrasting number 1 versus number 2, number 1 had these really important parentheses, where number 2 does not have parentheses around this x. So this plus 3 means up 3. It's on the outside. We know the base value is 1/9, which makes this a decay problem. And then we have one more transformation with this 5 out in front, and that would be a vertical stretch of 5. Okay? So from the very beginning, we need to be thinking this is decay, and decay means we're going down, and we're going to hit that turning point and flatten out and go to the right. Okay, so there's the original. If we want to do the table again, this would be x, y, and we got 1, 0. My b value is 1/9, so if I plug in 1/9, we get 1. And then if I raise, or if I want a result of -1, that means I had to have plugged in 9. Okay, the way I'm doing that is I'm relating back to these other points and how we got those other points from exponential to logarithmic. Okay, so that's where those random numbers seem like they're coming from, but they're coming from right here. Okay, and so when we go to graph that, we got 1, 0, and we have 1/9, 1. So that means I'm going to be really close to the y-axis here. And again, this is for the parent. And then we have 9, -1. And so we're really close to that x-axis or that y-axis. We're going down, we're going down. We're going to hit our points, and then we're going to flatten out just like that. Okay. I know I drew it where it looks like it actually completely goes perfectly flat, like horizontal, but it doesn't. It's actually, you know what? I'm just going to redraw it. Let's make sure we draw this appropriately. So we're going, and I'm still going down just very, 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 very slowly. That's a better drawing. Okay, so it's not that it's all of a sudden going to go perfectly horizontal. It's going to very, very tiny, very, very slowly go down, but keep going down forever. Okay, so now we need to apply our transformations that we have. So our up 3 affects the y value. Vertical stretch of 5 affects the y value. And we don't have anything that's going to affect the x. Okay, so PEMDAS still needs to be applied for our transformations. Vertical stretch is multiplying, so we need to multiply everything by 5 first. So 0 times 5 is still 0. 1 times 5 is 5. And then that would be negative 5. Then we're going to go up 3, because again, that affects the y value. So from 0, we'll go plus 3, and plus 3. And then we can graph. So we have x is 1 comma 3. Then we have 1/9 comma 8. So that's going to be like way up there at the top. And then we have 9 comma negative 2. 9 comma negative 2. Okay. And so our graph is going to be hugging that y-axis again, except now we're going to kind of deviate and go farther from it quicker. And our curve should look something about like that. Okay. So our new turning point is at 1 comma 3. Vertical asymptote did not move because I didn't push this graph left or right anything. So the vertical asymptote did not move. So it's still at x equals 0. The domain is still 0 to infinity, and the range is negative infinity to infinity. Okay, so that brings me to a good point about the differences in exponential and logarithmic. When the asymptote changes, so for logarithmic, it's vertical at x equals 0. Well, there's only one transformation that's going to affect whether or not we move left or right, and that's going to affect our range. Okay, so if we move left and right with a vertical asymptote, it's physically going to push it to a different spot, which would affect, in this case, our domain. Okay, if we go back to an exponential function up here, and I think about like this equation in blue, well, there is an horizontal asymptote at y equals 0 that it's not going to cross. But if I push this left and right, well, it's not going to affect the horizontal asymptote. So when the transformations are for exponential and it's like plus 4, well, then I'd have to push the entire horizontal asymptote up 4. So my point is, if you can remember exponential versus logarithmic and which one has the type of asymptote, knowing that that line could be physically pushed left and right or up and down will help you determine the domain and range for that function as well as graphing it. Okay, so we're going on to number 3. This is our last one that we're going to graph. Okay, so we have f of x equals negative log base 5 of x minus 3 plus 2. And so we have log base 5. 5 is bigger than 1, so this is going to be a growth. And so right away our graph's going to look something like that from the beginning. That's the parent. Then we have to label our transformations. So the plus 2 is up 2. This minus 3 is right 3. Inside the parentheses does the opposite. And then this negative means that we are reflecting over a very specific axis, which would be the x-axis. X-axis is the one that's out in front when the negative is out in front. Okay, so the parent, we have the turning point at 1 comma 0. So if I plug in 1 to just, and this would be like log base 5 of x is what I'm saying as the parent with no transformations. If I plug in 1, we should get 0. If I plug in 5, we'll get 1. And if I plug in 1/5, you get negative 1. Okay? And we need to be able to memorize those kinds of relationships. And again, that's the other points back up at the table on the first page. Okay? Now we're going to, we can graph it, 1 comma 0, we got 5 comma 1, and sorry, and 1/5 negative 1. So look right there. And so we're going up, we're going to hit this point, flatten out and go about like that. Okay. And again, for this parent logarithm, we have a vertical asymptote at x equals 0. That's the line we're not allowed to cross. Okay, so if we're applying our transformations, this affects the x value, this one affects the y value, and then if I'm reflecting over the x-axis, well, if I'm reflecting over, that means my y value is changing, and so we're going to use that for the y. Okay, so right 3 affects the x, so we're going to add 3, so that's 4, 8, and let's see, 3 over 1 plus 1/5 would be, that turns into, oh, this turns into 5 over, oh goodness, 15 over 5. So that would be 16/5. So this would be 16/5, which is just past 3. Okay. And let's see. So again, PEMDAS, when you're applying transformations, definitely applies. Well, we're multiplying by the negative here, and we're adding 2 there, so the multiplying wins. So negative times 0 is still 0. That becomes -1, and that becomes +1. And so then when we go up 2, we're going to do 2 and 1 and 3. Okay, so now we just need to go graph, and we should be in a good spot. So we're going to be at 4, 2. Then we have 8, 1. And then 16/5 is just past 3. So we're at a little past 3, 3, which should be like right there. And then we need to think about where our vertical asymptote would be. Well, I pushed this whole graph to the right 3 and up 2. Well, only one of those affects my current vertical asymptote right here. Only one of those would change that. And it's the one that's right 3. So I'm pushing this whole thing, pushing the whole vertical asymptote to the right 3. And so now we're going to be at x equals 3. And we reflect it over the x-axis. So it went from a exponential growth problem and then became an exponential decay. So when I circled this a minute ago, it was true, but our graph actually looks the opposite, which is kind of interesting. But, so our turning point would now be at 4, 2. Our vertical asymptote now is at x equals 3. The domain is based off of this vertical asymptote, so that's going to be 3, infinity. And then the range is everything. Okay, and I know I'm going through some of these kind of quick, but that in essence is how to graph logarithmic functions. They're very similar to exponential. You just kind of have to flip-flop the important pieces like the turning points and some of those other points and the asymptotes. You need to switch kind of what they mean in your brain to help you graph the other one. Okay, so the last thing we're doing is going to be converting from exponential to logarithmic and logarithmic to exponential. And there is one phrase that you're going to need to remember. Okay, and it's LRM, which stands for left, right, middle. Okay, you don't have to write it that way. You could just write left, right, middle. But this pattern, left, right, middle, is going to be, hopefully make it really easy to go from both directions, from exponential to logarithmic and logarithmic to exponential. So let me show you what I mean. So number 4 says we need to rewrite from exponential into logarithmic. We're changing them into logarithmic. So this would be the number on the left. This would be the number on the right. And this exponent is the number in the middle. So if I'm changing it into logarithmic, we're going to put log, base, the number on the left, which is 2, of the number on the right, which is 1/8, equals the number in the middle, equals -3, and then that's the equation. So left, right, middle. If we go to number 5 and do the same thing, Number 5 would be, there's the number on the left, that would be on the right, this would be in the middle. So we're going into logarithmic world. So there's log base, which would be 8 on the left, of 64, which is on the right, and then equals 2 that's in the middle. Left, right, middle. And so that'd be log base 8 of 64 is equal to 2. And then number 6, one last time you'd put log, left, right, middle. So that's log base 5 of 1/125, 1 over 125 is equal to -3. Okay, so that'd be the new equation. What's tricky at times is going the other direction, and I'll show you what I mean by what I think is tricky about some of these if you mess up your left, right, middle. When you're in logarithmic going to exponential, it might actually be even easier. Number on the left raised to the third power equals the number in the middle, 64. 4/3 is 64. That's true. And then we have number on the left, which is 2. So base of 2 raised to the -1/4 power, number on the right, is equal to the number in the middle, 1/16. And that's a true statement. We rewrote it. And then we have number 9. Number on the left would be 12. Number on the right would be 0. And the number in the middle would be 1. And so this is also true. Anything raised to the 0 power is 1. Okay. What can be tricky about some of these is when applying left, right, middle, the format that the original problem gives you is extremely important. It has to match the exact format that these are given. So let me give you an example of one that wouldn't work. If I flip-flopped these and I did 1 over 125 equals 5 to the -3, you cannot do left, right, middle for this. Because then I would say log of 1 over 125 of -3 equals 5. Our pieces are not in the same order, so you can't do it that way. So you have to make sure when you're doing left, right, middle that the base to the power is equal to the number, and it has to match that format. The same thing is true for logarithmic. If I rewrite this and I put the 0 in the front, and I do 0 equals log of 12 of 1, well, this is the number on the left, this is the number on the right, and that's in the middle. So that would be 0 raised to the first equals 12, which is not true, and that would be really bad. So the same thing is true for logarithmic. You have to make sure that it's in this format. Log of whatever base of x equals the y value, where the log base x is on the left equals y on the right side. Okay, so the structure that before you apply left, right, middle, the structure that it looks like, the formatting it looks like, is something that's really important. Okay, so be really careful about that. So if we go to our next examples, we're going to actually be finding how much they are. Okay, we're going to be determining their actual values. And so when you're in logarithmic world, in the logarithmic format, sometimes it's kind of weird to figure out what the answer would be. So we're looking for, what is that equal to? And so sometimes for me is I like writing them back into exponential because it's easier for me to say, oh, what 4 to the something is equal to 1/16. That makes a little more sense in my brain. I like exponential world a little bit better. And so if you notice 4, and obviously y'all know 4 squared would be 16, but now I'm in the denominator, so I need 4 to the -2 to be 1/16. And so the answer for this is -2. Because that 2 again pushes it to the denominator. It pushes this 4 to the bottom. And then when you square it, that's what makes the 16. Okay, so back on to number 11. If we were doing like left, right, middle, it'd be 25 on the left, raised to the something power is just 5. And so if I'm thinking, I need to simplify this equation, well, I need 25 to become smaller. So that does not mean you need to raise it to a negative power. It means you need to raise it to an exponent that's between 0 and 1. Well, we did a whole lot in Unit 7 about, well, when you take the square root of a number, that's the same thing as raising that to a very specific power. It could be 1/2, or if we were doing the cube root or fourth root or fifth root, it could be 1/3 or 1/4 or 1/5, but it's the exponent. So this exponent, x, has to be equal to 1/2. That's the only exponent that we could use for that. That would get us from 25 to 5. So log base 25 of 5 is 1/2. 12, again, I would rewrite it into exponential. This would be 1/5 raised to the something is equal to 3,125. Okay. In your brain, I would be thinking, I am starting with a fraction as my base, and I am becoming a whole number, a number that's not a fraction, a number bigger than 1. So in my brain, I need to think, well, then I need to make b at least a negative, because that negative would cause, and it would change this 1/5 to turn into 5 to the negative x. And then I need to think, well, 5 to the what power is going to get me 3125? Okay, and you're probably thinking, well, that's crazy to do in my head, but if we know it's a true statement, like I know x is a number, and we're doing this without a calculator, so I think it's fair to assume that it's going to be a whole number. Well, I know 5 squared is 25, 5 cubed is 125. Well, I know we did the other day in class where we did 5 to the 4th is 625. Well, if I'm going to do 5 to the 5th, and this is kind of like rounded down 600 times 5, well, 600 times 5 is 0, 0 would be 3,000. And so 5 to the 5th does make that 3125 that we need, but I started with 1/5. And so my answer is going to end up being not 5, but -5, because I'm trying to take 1/5 to the something power to get positive 135, and the only way to do that would be with -5 as my answer. Okay, so with all that being said, there are two special logarithms, two very special ones. For all these problems that we've had, I've been trying to make a big deal about noticing what the base is and writing an exponential form, and so I just circled the 3 bases for 10, 11, and 12. But if we look at this, there is no base. There's no number written there. When there's no number written, it is an implied base 10. So that'd be the same thing as writing log base 10 of x. Okay? It is implied. If there is no number there, every single time it's going to be 10. For the other special case, it's really specific to ln. Okay? ln is the natural log of x. Okay? And it has a base value of e. You should never ever write it this way, but this is the same thing as log base e of x. Okay? E is a very special number that we can get into a different time. It's actually on your calculator. It's just a really specific base value. But for our sake right now, we need to know that ln stands for the natural log, and know that that represents the number e. Because that is a number, not a variable, that's a number. Okay, so if I look at number 13, and I need to evaluate, there is no base written, which means it has to be a 10. So this is like saying 10 to the what equals 1,000. Well, we know 10 times 10 is 100. So 100 times another 10 would be 1,000. So that means x has to be 3. It's going to have to be a 3. Off to number 14. If we again do left, right, middle, this would be 7 to the something equals 1. Well, anything raised to a specific power always results in 1. Well, that special number is always 0. So log base 7 of 1 is always 0. 15, We have log base 3 of 81. So that'd be 3 to the something equals 81. And so 3 times 3 is 9. And 3 times 3 makes another 9, and 9 times 9 is 81, so that has to be 4. So log base 3 of 81 is 4. 4 would be the exponent that we would need to make 3 become 81. Okay? And then we have some special inverse properties at the very, very end. Okay, inverse properties. So again, we talked about a minute ago how exponential functions and logarithmic functions, they're inverses, which means they reflect over the line in y equals x, and we could do all their graphs and stuff. Well, when they're written in a really specific format, since they're inverses, they kind of cancel each other out. Because if you raise something to its own inverse, well, they cancel. It's kind of like the other day, I think we did a problem where we had, what did we do? We had like x raised to the 3/4 power equals, and it was like, I don't know, 16. And I made a point about if you raise this and do power to power, and you multiply it or raise it to its own reciprocal, well, then those are going to cancel. And these cancel out and just become x. Well, that's kind of the similar idea to what we're doing here. If I take 3, and 3 would be my base value for number 16. If I take 3 as my base, and I raise it to its own inverse, the 3 and the log base 3 cancel, and the whole thing just is x. It all just simplifies, and the x comes down. Okay, that's going to be a really important idea to know. Okay, and the reason that kind of works, and I'll write it in a different way. The reason that kind of works is if I say 3 to the log base 3 of x is equal to a for answer. And if I rewrite that in logarithmic form, well, then it would be the number on the left, so that'd be log base 3 of the number on the right, a, has to be equal to the exponent, which we found no, and it tells us is log base 3 of x. Well, if these things are the same thing, log base 3 and log base 3, then this value and that value have to be the same thing because they're equal. So that's kind of what's going on in the background. I'm fine if you do not show this, but we need to be able to recognize and say, oh, this is base 3 being raised to its own inverse. Those cancel and just become an a. Or I'm sorry, an x. 17, there is a important logarithmic property going on here as well, where if these two numbers are the same thing, they also cancel, and the whole thing is just x. And the whole thing is just x. Okay, so that's another property, and we haven't really put words to it, but if those are the same number, they go away, the log goes away, the whole answer simplifies to just x. Okay, 18, we have that e, the natural log, e, is being raised to the natural log of 3x. Well, again, if we kind of thought about our left, right, middle idea and writing this in logarithmic form, then this would be the natural log of, we'll do a for answer, the natural log of a is equal to the natural log of 3x, which again, if the left and the right side are supposed to be equal and they have the same bases, that means the whole answer has to be 3x, because a answer equals 3x, they have to be the same. Okay, and then finally 19. 19, we have one more example where we need to change, and we're going to rewrite 8 to the x as this property actually up here on 17 that we just talked about. Well, I can rewrite 8 is equal to, and I want the base to be 2, and 2 to the third is the same thing. So 8 to the x is the same thing as 2 to the 3x. And so what ends up happening is I can rewrite the whole thing as log base 2 of 2 to the 3x. And now, just like we did up here on 17, since these numbers are the same, everything cancels, and the final answer is 3x for this as well. Okay? When I get back, we can go back over and talk about some of these rules, and if I need to explain them again, that's totally fine. But those in essence are some of the really important inverse properties that you need to know. All right. Let me know if you have any questions. But other than that, we are done.